Okay. All right, so we're going to cover material that will appear on exam 3. Do you have any specific suggestions of what to look at? Any problems that you're struggling with that you want me to present on? Okay. Why don't we take a look at some of the examples here. Here is exam 3. These are the, I think we looked at that. Let's look at find max. Let's do this one. So find the maximum value in a two-dimensional array. So rows and cols are defined elsewhere in the program. You don't have to define those. Let me go into, let's create a new folder here. So the problem is to implement and test that function right there. Now, as a stub, that won't compile because the function is declared as returning a double, but we don't have a return statement. So let's go ahead and return a 0. Oh, rows and cols are undefined. So in the exam, you're not going to have to define those, but I want to show you what that would look like in a running program. So we can use this const keyword. It means constant. It's not changing. Constant int rows. And by convention, these constants are named with uppercase letters, but that's not required. Just as an example there. Oops. But you wouldn't need to write this in the exam if I stated the problem the way I do here. The variables rows and cols are constants defined elsewhere in the program. You don't need to define them, just use them. Now this function here finds the largest number in the array. So let's, on the exam you wouldn't do this, but let's do this now. Let's create test data for this function. So we have an array A with rows and columns, but I think I'll do it like this. If I can remember how to do this. No, I'll do it like this. Rows, columns. So that statement right there creates a block of memory that has 12 integers in sequence. So a memory is like linear. It's addressable. Memory is addressable. Each byte in memory has a numeric address. And those numeric addresses are sequential. So you think of memory as being laid out, conceptually laid out as a linear sequence of numbered byte locations. But a two-dimensional array, it sort of gives you the illusion that the memory is sort of set up as a grid or a table. But in fact, it's really is sequence. I mean, physically, in memory, maybe it's not a linear structure, but in terms of the low-level operations performed by the CPU, the memory that's allocated for the array is just a linear sequence of values that are numbered. So let's put some numbers in there. Oops, two-dimensional. That's A of 0, A of 1. So we'll populate the first row, and there's 4 columns. There are 4 columns for the first row. And the second row has 4 columns. And the third row has 4 columns as well. The third row has index 2. And so these are the values. They're all -5. Let's put a -3 in there. Leave everything else at -5, just as a test. So we call this function find max A. This should return -3. That's the largest value. So we assert that find max returns -3 when we pass in A. Now that'll fail because we have a stub implemented. I just want to see if it compiles. It doesn't. Oh, this is a double. So it doesn't compile because A is a two-dimensional array of doubles, and we've declared A as an integer here. There we go. So these values are doubles, but we can list it like this. It's okay. You know, this is fine. And we can use integers there as well. So failed. Find max does not return -3. So the trick here is we need to iterate. We need to look at every value in the array and keep track of the biggest one we've seen so far. When we get to the end of the array, the biggest value we've seen so far must be the biggest value because we've seen everything. What's the biggest value we've seen so far? So we're going to iterate through the array. And here we test on the inside of the array. We want to see we're at a current row position and column position, I and j, and we want to compare that with the biggest value we've seen so far. Is what we're looking at now bigger than the biggest value we've seen so far? If it is, then we want to change the biggest value seen so far variable to equal the current value that we know is bigger than the previous one. And then at the end, we return that because we've seen everything. So the name of the variable represents kind of like the state of the algorithm at an intermediate point in time. So maybe we've looked through half of the data already. So we don't know the biggest value yet, but we know the biggest value we've seen so far. There's a total of 12 elements to look at. We've only looked at 6. But the biggest value we've seen so far is -5, say. But as we keep looking, we're going to update that number. And then when we get to the end, we've seen everything. So that now the name of the variable would be, you could change it. It's now the biggest value, the absolute biggest value in the array. But the name of this variable that I've chosen here represents how the algorithm works at an intermediate point in time. Now the trick is what to initialize this to. And here's the mistake that some people make. You're going to initialize it to something. Maybe you just put in a really low number. Or you put in a 0. Of course, 0 will fail for us because on purpose I chose all the values to be negative. So I wanted to test against this logical error here. What happens if every number in the array were negative? The biggest, then the max that the function returns is 0. So it turns out that it's good, or that it works, if we just set the biggest value seen so far to one of the values in the array, and we'll get a valid number at that point. So just take the first value, not I and j, sorry, 0, 0. Just take the first value in the array. So now we're initializing our record-keeping variable to -5 in this case. There we got it. And we could add more tests if we like, but I'm not going to go that route. And if this variable name is too long for you, you can use a shorter name. Well, maybe max. Because we're supposed to find the max, so let's just call this variable the max. So this max is, the name now reflects what the value will be at the end of the algorithm, not at an intermediate point in the running of the algorithm. But it's a little easier to read. It's a shorter name. And the name also reflects the function name, find max. When we find max, we return max. Makes it a little, it's somewhat readable. So that's this one. Now, on the exam, you don't have to do this test code. And you don't need to write down this function declaration, but you can if you like. You don't need to declare these variables. Just write this here. That's the implementation of the function. Let's see. That's what it looked like. Well, look at that, exactly. Oh, I called it int here, didn't I? That's a mistake. I'll have to change that later. This is a double. So this code will not compile. That's we saw that already. This is not an int, that should be a double. What about this search function? Find the location of k and v. Did we look at this already? Is this something you want to look at? Is this all right? All right, so this search means find k and v. But v is, we saw this already, right? Or not? So skip this one. Skip this one? Or do this one? Do it. All right, do it. Do not use binary search because the values are not in order. Or do not assume that they are in order. So here's an example, -2, 4, 18, 6, -10. Those are not in order. So that's an example of a vector where the values are not in order. We cannot use binary search. We have to look at everything. And here's an example for k. Well, we want to find 1. Well, 1's not in there, but we don't know until we look at every number. So in the worst case, this algorithm requires us to look at every value in the vector. If the vector is of size n, we have a loop that runs n times. So we say that that has time complexity O n. You'll get that later. I'm not going to define that now, but that's later. If you go on with computer science courses, you'll study this thing called time complexity, where you measure how much computation is needed, how much time is needed, how many instructions are needed to execute in order to solve a problem. And here, the number of instructions that to execute to solve this problem is some proportion or some multiple of n, the size of the number of values in the vector. If the vector has 1,000,000 items in it, we have to run a loop 1,000,000 times, and that could generate so many machine instructions that are repeated 1,000,000 times. So the number of instructions that are executed would be some factor of 1,000,000. All right, so let's do this one. This is search. That's not me, is it? Okay. Here's the function declaration. And we need to include the vector header. And we're going to return a value. I'm going to say return n. The function returns the index of the value in the vector. Otherwise, it returns -1. So what k is the value we're looking for. But what we return is the position of k and v. Or -1 if it's not there. So we have a vector of int. Let's push back 9. Actually, let's stick with the example. -2, 4, 18, 6, -10. -2, 4, 18, 6, -10. Whoops. -2, 4, 18, 6, -10. There it is. And then we, let's assert that when we search through V, looking for 1, that it must return -1 because it's not there. So it's a pretty straightforward problem. We just start the loop. Use the standard loop here. This you should have memorized, really. You start at 0. Don't let the index hit the size. If it does, then you're done with the loop. The loop condition should be false when the index equals the size of the vector. We don't want to check the position that equals the size number because we're 1 off because we started counting at 0. Then we increment the index. So we're looking for k in V. So if V of I is k, we found it. What do we return here? Let's see if anyone's paying attention. What do we return here?
Return I.
Huh?
Return
I, thank you. Yeah, sorry, my ears are bad. You did say I. And this is good. And what do we return here? Good, -1. Because we went through the loop. We never hit. This was never true. And so we looked at everything. That means, well, it's not there. So let's return -1. What is going on? How are we going to read that? Before I read that, I'll
define the vectors and int.
Oh, thank you. That's another mistake on the on my web page. This should be a vector of int. Thank you. There we go. So you really get the bugs out when you run it, right? So I have to fix those too. Now here's binary search. We did this one already. It takes some time to learn that one. Binary search. And what else do we have here? Flatten. We did that. I know that. Is strictly increasing. I think we did that last time. I think.
Did you do the first one?
Oh yeah, are identical. Yeah, let's do that one. That's good. We have two vectors, A and B. Are they identical? Return true if they're identical. If they're not identical, let's see, this one is max. I'll just do find max. If the vectors are identical, return true, otherwise return false. Oh, here we have a vector V. Here's another vector called W. Look at W. W and V are not the same because W has -10 is duplicated on the end there. The lengths are different. They have a different number of elements. So contain exactly the same elements in the same order. Well, they don't have exactly the same elements in the same order because W has one more element, even though it's a duplicate of the one before it. So this should return false. So if we call the function are identical with V and W, it should return false. All right, there we have our test code set up. Now, so what we'll do is we're going to have this loop that runs through each of the values, all the indices, and comparing, at index 0, comparing the value in A at 0 with the value in B at 0. Are they the same? Yes, they're the same. Okay, let's look at the next value. So we need to have a loop there to do that. So I starts at 0. I is strictly less than A dot size. By the way, we could use B dot size. Because to do this loop only makes sense if the two vectors have the same length, right? So otherwise, how are we going to compare elements if they don't have if they have different lengths? So before we even do anything else, let's check that. If A dot size is not equal to B dot size, then we don't have the right condition to move forward. There are different lengths. We're not going to be able to carry out our algorithm that compares the values. So we're going to return false at that point right off the bat. So if they have different sizes, we're done. They can't be identical. If they have the same size, then we can use A dot size or B dot size. It's the same number, so I'm just using A dot size because A comes first. And then what we want to do is compare what is in A at index I. Compare that with. Well, let me do it the wrong way first. I'm going to show you the wrong way. Let's suppose A of I equals B of I. What do? People in previous quarters, people would return true here. Oh, they're identical. Well, that means you wouldn't look at all the numbers. You would just look at the first number in both A and B and say, well, if those are the same, then the vectors are identical. Well, that's not true. We got to look at all the numbers. So we got to go all the way to the end. So what is a better choice here for comparison is, are they different? Because if they're different, then the vectors are not identical. We're going to return false right on the spot. We don't have to look at all the values because we found a pair that didn't match. And so we keep going. If we don't find a pair of values from A and B that are not equal, that means they're all equal. So we return true. It's the hard part of this problem. A lot of students don't, get that. Have to think about that. Test that in lab. See, make sure you get that to work right. And let's have another test here. Let's test the other side. Let's call popback on W. Now V and W, if popback removes the last element from a vector. Now that V and W are identical. So if we call the function now, R identical should return true. Let's try that. Looks good. You got it. I'm feeling more confident with those additional tests there. With that additional test, I feel more confident that we got it. And I guess this is okay. Now for the exam, this is sufficient right here. This code, just writing that down. You don't have to include all the other stuff. Unless I ask you for the test code, then you'll have to come up with the test code. And I always have at least one question where I ask you to write test code in the exam. Actually, it's always been one question. I always ask one question for test code. So this is called a predicate function. Predicate function means it returns true or false. I think from the terminology of symbolic logic, the term predicate means it's like a statement, like a true, false expression that's evaluated, an expression evaluated to true or false. You can think of this as an expression that evaluates to true or false. So this is an expression that evaluates to true or false. That also is an expression that evaluates to true or false. Those are Boolean expressions. And a function that returns a Boolean value is called a predicate function. But I don't hear that. I come across that word in textbooks, but not in practice. All right. What about we're here, right, inside arrays? Yeah. Is there anything in here you want to talk about? Any of these problems that you're working on that you had trouble with? Seven? We just did this one, right? Did I get that?
Yeah. Okay.
Yeah, all right. And is all zeros, count occurrences. I think we did this last time, right? Count occurrences. A vector insertion. Do you want to look at that one?
Yeah.
Huh? That one. All right, so suppose a vector v contains a sequence of integers ordered from lowest to highest. Like this. 3, 6, 7, 8, and 12. There's an example, a sequence of integers ordered from lowest to highest. Well, there's the example now, 3, 6, 7, and 12. Write a function called insert that takes this vector v as a first argument and an integer k as the second argument. The function inserts k into the vector so that it preserves the order of elements. For example, if v were 3, 6, 7, and 12, and k were 8, calling the function would result in 3, 6, 7, 8, 12, that vector. Apparently, there's an insert function built into the vector class, but we're not going to use that. We're going to implement it from scratch. Use test code to test. So let's do this one. I don't really need to be saving these functions when I mean this work, but I am anyway. All right, so let's see. Let's do insert 3, 6, 7, 8, and 12. So that's I like to do the test code early. 3, 6, 7, 8, and 12. 7, 8, and 12. There we go. And with this code, we call the function, which is insert, we insert into V the value 8. Was it 8? No. Oh, 3, 6, 7, and 12. 3, 6, 7, and 12. Sorry. 3, 6, 7, and 12. When we insert 8, now insert doesn't return anything. It's a void function. So it doesn't return anything. It just modifies V. Oh, this function is not going to work the way I declared it. Does anyone see the problem? It's a declaration error here. Something in the parameter list. The V.
You put an ampersand.
Exactly. It needs to be a reference. Very good. Because without the reference, without the ampersand, it's not a reference. And the compiler generates code that makes a copy of the vector. And then we operate on the copy. And then when we return from the function, we discard the copy. And then the calling code, nothing, the vector from the calling code didn't get modified. So we need to tell the compiler that not to make a copy, that let's use V as a reference to the object that's in the calling code. So after we insert 8, we'll have some assertions here. V of 0 should remain unchanged. It should be 3. And then we have V of 1, 2, 3, and 4. V of 1 should be 6. V of 2 is 7. V of 3 is now 8. And 12 is moved back into position 4. There we go. Now this will compile, because the stub here, we don't need a return statement for a void function. So this will compile and fail. There we go. So we didn't modify V. See, by compiling and running there and verifying that it fails, I'm testing the test code, right? It should fail. I want to see it fail. We got to test your test code. And now how do we insert this thing? Well, we need to make, when we created this vector here, it has size 4. We need to make it larger. And all we know at this point is to use a pushback. Let's push back K. So now in the example, if we push back K, then V is going to look like this. 3, 6, 7, 12, 8. Just to show what the example would look like. So now what we're going to do is we're going to go backwards in the vector and sort of exchange this K. We're gonna look at, we'll start in the last position, and we're going to look in front of it. So the last position contains the value that we just pushed. We're going to look at the value in front of it. If we're less than the value in front of it, then we're going to take the value in front of it and write it into the current position. And then I'm going to move my pointer, my index, to forward. And then now I'm at, this is my current position. I'm going to look at the position in front of me, and if that position is greater than 8, or K, then I'll move that value, 7, into my current position. But it's not in this case. That means we found the right spot. Actually, what I'm going to do is make it a little more interesting. The problem, I'm not moving enough. So I'm going to make this a 9. And this should be 8 and 9. I just want to change it out a little bit there. This is a better example. So the vector is originally in a sorted order, but now when we push back that value k, it's no longer sorted. So one way to think about it conceptually is that we're going to swap these two values. As long as the value on the right is smaller than the value on the left, we're going to swap. So we swap these two to get them in the right order. And then we'll have another vector. After we swap those two, the vector is going to look like this. That's when we do the swap. And now we're going to look at 8 and 9. We're going to compare these two and swap those two. Now we're going to look at this pair, 6 and 8, and we're going to say, whoa, wait a minute. 6 is less than 8, and everything before 6 is less than 6 because it's a sorted vector. So we're done. We just do this swapping, pairwise swapping, until we hit the point where the value in the front is less than the value where we're at. So that's the algorithm. That's how the processing will look. So the loop is going to be tricky here. The loop is going to be, we can't start, we've got to start at the end there, right? So I'm going to take v dot size minus 1. That's the starting point in the loop. So this looks a little different than the other loops. We could use a while loop, but a for loop works fine here as well. And then we have the loop condition. Well, we can't do any swapping if I hit 0, then we can't look at position minus 1 because it's not there. So the smallest that I can get to is 1, because we have to subtract 1 to get the index of the position we need to examine. So, and then we're going down, so we got to decrement I. And then, so here's the test. If, remember, we're looking at these pairs. You know, v of I compared to v of I minus 1. So v of I minus 1 has to make sense. That's why I has to be strictly greater than 0, because when I hits 1, we're going to get 0. But if I hit 0, we couldn't look at v of minus 1. So let's go ahead and look at this. This is if v of I, we'll do it like this. If v of I minus 1, if this is bigger, no. I'm going to do it like this. If v of I minus 1 is smaller than, in my head, I went through all kinds of possibilities, right? And I said, well, what's going to make the code the smallest? Right? And I just changed, you see I changed my mind there? Because I went through a bunch of very quickly in my mind there, I went through a bunch of possibilities, and I think this is going to make the code the smallest. You're going to go slower than me, because you haven't done this as many years as I have. So v of I minus 1, we're going to compare that to v of I. If v of I minus 1 is less than v of I, that's that situation where, I is 2, so v of I is 8. We're going to compare v of 2 with v of 1, which is 6. And 6 is less than 8, so we're done, right? We're done right there. So if v of I minus 1 is less than v of I in this processing loop, what do we do? What do we do? And maybe I'm going too slow for some of you, and for others I'm going too fast, right? So, well, if v of I minus 1 is less than v of I, we're done. Going to get out of there. Oops, we got to spell it right. Otherwise, we need to rearrange them. V of I needs to get the bigger value. And v of I minus 1 needs to get the smaller value. Which happens to be k. You know, there's many ways to writing this algorithm out, and this is just one way. Now, what happens if I hits 0? No, we'll try that actually. Let's do that. What happens if I hits 0? So I'm going to let's go ahead and insert. Let's insert a 1. That means v of 0 is now 1. And v of 1 is 3. All the way down. So we move everything up. So if here's test code that tests a boundary case. Let's insert a number that slides all the way to the front of the vector. That's called a boundary case. Another boundary case, let's insert a number that sits at the end of the vector. That doesn't move the vector at all. I don't have that in there right now, but we should add that as well. So there's 2 boundary cases. Those are called boundary cases. What happens when we insert the 1? That means 1 is always less than any number we compare to. So this will never be true. We'll never find a value. So 1 is in here. And we're never going to find a point where the value before 1 is less than 1. We never get there. And, and think about it, when we're at the end of the loop, when I is at 1, when I is at 1, and v of 1 is 1, and v of 0 is 3. And then we're going to copy the 3 into position 1, and then we're going to write the 1 into position 0. So 1 goes into position 0, but we're done, right? Once we put 1 into position 0, we're finished. And the loop condition is now false. Well, when we hit the bottom of the loop, we'll decrement I, it goes to 0. The loop condition is false, so we're done. So we just return. And by the way, for a void function, I don't have to put return at the bottom of the function. It's an automatic return. But we could put it there if we like. Let's test that. There it is. So that's it. And normally we leave that one out. So this is a technique that uses swapping. You don't actually have to do the swapping. This line here is optional. Because we could have done it like this. Let me show you. Because what's in v of I is always k. So just put it like this. And then, I don't want to get into that. I will leave it like this. I want to keep it simple. So once again, on the exam, this would be the answer. This one's a little bit more involved than the other ones, but I think it's doable. Does that sound all right? We're all set? I got this, we have a few minutes left. I need for you to fill out this evaluation form for the class. And I'll step outside the